Welcome to The Explainer. Today, we're diving straight into the hidden machinery behind something you probably do a dozen times a day without even a second thought. We are going to unpack the architecture of a modern URL shortener. To do this, we're pulling from some fantastic source material, a comprehensive guide called Building RESTful Web Services with Go by Narenya Lavula, alongside an academic research paper on a system called SnapLink, which was published in the International Journal of Advanced Research in Science, Communication, and Technology.
So what actually happens in the 12 milliseconds after you click a short link? 12 milliseconds is literally a fraction of the time it takes you to blink. But in that tiny microscopic window, a massive, globally scaled infrastructure springs into action. We just expect a link to work instantly, right? But as we pull back the curtain today, you're going to see that a simple click sets off this wild, rapid-fire sequence of security checks, database queries, math algorithms, and data analytics.
Here is our roadmap for today. We'll start with the URL shortener unveiled, then look at REST APIs as the messengers, the base 62 shortening algorithm, the power of caching, click analytics, and finally, designing for scale. All right, part 1, the URL shortener unveiled. Let's take a look under the hood of a simple click. If you think a URL shortener is just a basic text compressor, you might want to think again. The SnapLink research clearly shows that modern URL shorteners are actually comprehensive data and security engines. They don't just magically chop down a long string of text, they're highly robust routing applications. They securely authenticate the users creating the links, they generate memorable slugs, that's the short part of the link at the end, and they quietly track every single piece of data surrounding a click. It's basically an enterprise-level tool completely disguised as a simple, everyday utility. Moving right along to part 2, REST APIs, the messengers connecting the web. Let's talk about the architectural layer and how the front end actually talks to the database. As detailed in the textbook Building RESTful Web Services with Go, REST APIs are essentially the universal messengers of the internet. They rely on standard HTTP verbs, things like get to retrieve data and post to send new data. So when you submit a long URL to be shortened, you're making a post request. When someone actually clicks your shortened link later, their browser makes a GET request to find the original destination. It's just an incredibly clean, standardized way to handle requests securely, even at a massive scale. So let's actually map out that flow based on the SnapLink architecture. First, a user registers and logs in. To keep things secure, the backend generates a JSON Web Token, or JWT. This is absolutely crucial because it ensures only authorized users can create and manage their links. Step 2, that authenticated user submits their long URL. Step 3, the link goes live out into the wild, the public clicks it, and that triggers the routing engine. And finally, Step 4, almost completely invisibly to the user, the system tracks all the analytics of that specific click. Now, for part 3, the base 62 shortening algorithm. This is the core engine, the actual math that performs the magic of turning a massive web address into just 6 or 7 characters. Both of our sources, the Go API textbook and the SnapLink paper, point to the base 62 encoding algorithm as the absolute gold standard for this. Here's how it works. When a new URL gets saved to the database, it's assigned a unique, massive numerical ID. The base 62 algorithm then takes that giant number and translates it using exactly 62 characters. That's 26 lowercase letters, 26 uppercase letters, and 10 digits. It takes this giant database ID and compresses it into a super short, highly unique alphanumerical string. And boom, that becomes your URL slug. What is truly mind-blowing here is the sheer scale this math unlocks for us. By using just a 6 to 7 character string in base 62, you instantly get 56.8 billion unique combinations. Talk about storage efficiency. The researchers behind SnapLink tested this heavily, and they found an extraordinarily low collision rate of just 0.02%. That means 2 links accidentally generating the exact same slug is incredibly rare. But hey, even when it does happen, the system has this built-in retry logic that resolves the conflict in just 2 to 3 attempts, and the user never even notices. Which brings us to part 4, the power of caching and the absolute need for speed. Because when you're dealing with billion link databases, querying that database for every single click becomes a huge bottleneck. So the takeaway here is that caching is absolutely mandatory if you want a good user experience. The SnapLink researchers ran the performance tests, and the results are honestly pretty stark. Doing a standard database lookup to find an original URL took them 38 milliseconds. But by layering in a Redis cache, they dropped that down to just 12 milliseconds. That is over a 300% improvement in speed.
It's quite literally the difference between a link feeling a bit laggy and feeling completely instantaneous.
Think of caching like a high-speed temporary memory bank. Instead of digging through the heavy main database like PostgreSQL or MySQL, every time a popular link is clicked, Redis just stores the most frequently accessed URLs right there in the system's working memory. In the SnapLink architecture, they set this up with a 24-hour time to live or TTL. So if a link suddenly goes viral, the system isn't slamming the database thousands of times a second, it's just instantly handing out the destination directly from the Redis cache.
Let's pivot to part 5, beyond redirects, looking at click analytics. Because really, the redirect is just the utility, but the data, that is the business.
The front end of the SnapLink app is built using the React framework, and having a clean interface is essential. Why? Because users aren't just there to shorten a link, they're there to manage campaigns. A massive draw for any modern URL shortener is the dashboard, where users can dive into comprehensive click statistics, monitor their traffic, and manage their whole portfolio of links.
And honestly, user preference dictates a lot of the feature set. The SnapLink study dropped a really fascinating stat. 95% of users actually preferred creating their own custom slugs rather than using those auto-generated base 62 strings. This really goes to show that for the end user, these tools are mostly about branding, marketing, and keeping control over their digital presence, much more than just saving some character space on social media.
On top of that, the researchers found that 87% of users regularly returned just to view their click statistics. The analytics engine, which tracks exactly when a link was clicked, where in the world it was clicked from, and even what browser was used, is just as vital to the product's success as the redirection itself. It totally transforms a simple routing tool into a high-powered marketing asset.
All right, our final section, part 6, designing for scale. Let's put this whole puzzle together. How do we ensure this system doesn't just crash and burn when a link is posted to a massive audience?
Let's look at the full stack to see how these components build out a complete bulletproof architecture. To reach enterprise-level scale, you need highly specialized tools at every single layer. You've got React handling a snappy front end. You have a robust backend API. This could be built in Java with Spring Boot like they did in the SnapLink project, or in Go, which our textbook source really praises for handling highly scalable concurrent operations. Then, for reliable data storage, you use relational databases like PostgreSQL or MySQL. And finally, layered right on top of that database is Redis, acting as your high-speed caching safety net.
And let me tell you, this specific architecture delivers. During their load testing, the SnapLink system successfully handled 2,450 requests per second. They tested this with 500 concurrent users hitting the system all at the exact same time, and they recorded 0 errors. 0. That is the very definition of production-ready scalability.
But pulling off 2,450 requests per second with 0 errors doesn't just happen by accident. It takes a harmony of optimization techniques. First, proper database indexing ensures that even with tens of thousands of records, looking up a slug takes under 5 milliseconds. Second, as we touched on, Redis caching bypasses that database latency entirely. Third, and I love this one, async processing is used for the analytics. So when you click a link, it shoots you to the destination instantly on one thread, while a completely separate background thread quietly records the click data. The tracking literally never slows down the user. Finally, connection pooling efficiently manages the traffic between the backend and the database so nothing gets overloaded. So that leaves us with a pretty wild thought to chew on. We'd take a short 6-character link completely for granted, for sure. But behind that tiny slug is this vast world of base 62 mathematics, high-speed memory caching, JWT security protocols, and asynchronous data tracking. It's this beautifully complex orchestration, all happening in 12 milliseconds. The next time you click a short link, ask yourself, if a utility this simple requires this much brilliant engineering, what invisible, highly optimized complexities are powering the rest of your daily digital life? Thanks so much for joining me on this explainer, and keep questioning the technology around you.